Let's start with the quantities of kinematics. We'll start with position, distance, and displacement. So position is the location of an object in a coordinate system. So an object at point A has a position vector that goes from the origin to point A. And we tend to use in 2 dimensions the letter R with an arrow symbol on the top. So that's the position vector R sub A. If we then go to point B, we see the position vector pointing to us at point B. And there's the position at C. Now, if we consider the path from A to C having gone first to point B, we get that the distance traveled is the actual length of the path traveled, all positive without regard to direction. We literally just measure the path length that we traveled. On the other hand, our displacement is an arrow or vector that points from the initial starting point A to the final point C, regardless of having gone to point B at some time in the middle. In fact, the displacement vector is the change in position, the final position minus the initial position, which graphically is an arrow that starts at A and ends up at C. Here's a one-dimensional example. We'll start at x equal 10. We'll go to x equal 20. And finally to x equal 5. Some of these quantities here are the final position is x equal 5, right? The initial position was x equal 10. I'm not putting units in this example. But the distance traveled depends on the actual path, right? We went from 10 to 20, then to 5. All distance counts as positive, so we went a total of 25 units. But the displacement is minus 5. We went from 10 to 5. So we went 5, but to the left, so minus 5. The next group of quantities, velocity, speed, average velocity, average speed, sound a little similar, but they're different. Let's look at average velocity first. Average velocity is a displacement over time. So average velocity doesn't care about the path in between, right? You would just literally look at the starting point, the ending point, and take that displacement and divide by the time. Whereas average speed is the distance traveled over the time, right? Average velocity is a vector, average speed is a scalar. Now, velocity is like an average velocity, but for a very, very small time increment. And if we take a delta something, a delta t, and we consider it very, very small, arbitrarily small, infinitesimally small, a differential, indeed, that leads to differential calculus, right? A dt is a time element. It's a small part of time. In any case, velocity at a point is like an average velocity over a tiny, tiny, small time interval at that around that time we're concerned with. Speed is the magnitude or absolute value of the velocity. And let's look at that along a straight line and then along a curve. So if an object moves along a straight line, at some point in between, the velocity is like a small displacement, which I'll call a path element, over the time. And along a curve, we would get the same idea, that at some point in the middle where we might be interested in velocity, we would have a small displacement or path element divided by a time element. The takeaway is that since your displacement is always along your path, whether it's straight or curved, we refer to that as tangent to your path. A tangent line is like a line that just touches your path, and geometrically it sort of has the same slope. But your velocity being a displacement over a time is always tangent to your path. Now here's a one-dimensional example, but let's rotate that vertical, and this is common with motion graphs for one-dimensional problems. We'll also assume the speed is 2.5 meters per second. And we'll show the previous data in the previous one-dimensional example, where we started at x equal 10, we went up to x equal 20, and then we came down to x equal 5. Now again, the motion is all vertical here. It's on the number line, but the number line was rotated vertically so we can see a time axis. So we're starting to see that, we said the speed was 2.5 meters per second, and sure enough, for that first segment from x equal 10 to x equal 20, we went 10 meters in 4 seconds. 10 meters divided by 4 seconds is 2.5 meters per second. And then for the last 6 seconds, we went 15 meters. And yes, 15 meters over 6 seconds is also 2.5 meters per second. On the first 4 seconds, though, we're going away from the origin. We have a positive velocity. And in the last 6 seconds, we're heading toward the origin. We have a negative velocity. Lastly, we look at acceleration and average acceleration. So acceleration, just like velocity is a measure of how your position changes, acceleration is a measure of how your velocity changes. So if I had an object moving along a straight line, there's essentially 3 cases. Either I'm moving along the straight line at a constant speed and constant direction, constant velocity, so I have no acceleration. Or I increased my speed, in which case my acceleration has to be in the same direction as my velocity. Or I could have decreased my speed, so my acceleration was opposite in direction to my velocity, and I slowed down. Now, going around a curve is a little different. It's similar but different. Even at a constant speed, our velocity is changing direction. So even if we're traveling at a constant speed, we always will have an acceleration moving on a curve. And there's always that acceleration pointed in toward the center of curvature of the path. And actually, we can combine these ideas of acceleration causing increases and decreases in speed, and acceleration causing us to change our direction. If we look at the tangential direction in this diagram, right, that is the direction we're traveling, and our velocity arrow at that instant is shown as red. And even at a constant speed, we would have an acceleration pointing into the center of the circle, and that's known as the centripetal direction. Right, so the tangential direction is along our path. The centripetal direction is perpendicular and in toward the center of the circle, or center of curvature. Now, if I was increasing my speed around a curve, I would have to have an acceleration component. We'll discuss components and vectors very soon, but I'll just say that the acceleration vector, the blue arrow, would have to have sort of a projection or component along the tangential direction for us to be increasing our speed. And if we were decreasing our speed, that tangential acceleration would be in the opposite direction to our velocity. In both cases, though, there is always a centripetal acceleration because we are moving around a curve. And that's the beginning of these concepts of position, velocity, and acceleration.